Hello, welcome to one more lecture of this short tutorial series where we are showing some topics, and now is a differential equation, how we solve, how important are the differential equations, and so on. And in the last lecture we were talking about Laplace transform for solving differential equation. And I remember we have shown to you that we have a differential equation that the main goal is to determine a function. Here I call y of x. And, you know, by doing some transformation, what was a differential equation is now an algebraic equation. And the algebraic equation, you know, everybody knows how to solve. It's just to put eliminate the incognita, which will be a function, and determine. But this function, now we solve then this algebraic equation, and then we return doing the inverse transformation to get the solution. So this is a very powerful method that's called the Laplace transform method, and it relies on the fact that you transform a differential equation in an algebraic equation, and we all know that's easier to solve an algebraic equation. And then we define what is a Laplace transform of a function. Given a function, the Laplace transform goes from the incognita function, from the variable, to a reciprocal variable. So S now is like a mapping of the function f of t, but now in another space, the reciprocal space of time. And then I gave you some examples where this is important, like going from time domain to frequency domain, or going from space domain to reciprocal space domain, which are important in structures, in many things. And the inverse transform is the opposite, right? Once we have the Laplace transform of a function, we can identify this function. So this is a kind of a mathematical expression to say that this function is the function which Laplace transform is f of s. And we did a few examples, nice examples of different functions and their respective Laplace transform. And then we have a very nice table here with a few of the most important Laplace transform that we needed to consider, starting by power law type of functions, to exponential or trigonometrical function, or even hyperbolic trigonometric function. So once we have this table, we are able to do the transform of the equation. And then we rely on a few different properties. To use the Laplace transform to solve differential equation, we rely in a few properties. And the most important property is that the Laplace transform of the derivative of a function is related to the Laplace transform of the function itself. If we know the initial conditions, if we know the value of the function in the starting point, in 0. Equivalent, we can know that the Laplace transform of the second derivative is actually related to the Laplace transform of the function. But then we needed to know two initial conditions, the value of the function and the value of its derivative at the initial condition. And the Laplace transform of a derivative is just s times the Laplace transform of the function minus the initial condition. And the second derivative is s squared minus s, and so on. And then we were able to generalize. We generalized this by saying that the Laplace transform of any order derivative of a function is related exclusively to the Laplace transform of the function itself, times powers of this new variable s, which is the reciprocal space variable that we consider in the function. So you see, by knowing the initial conditions, which is the value of the function, the first derivative, second, we can get the Laplace transform of any order derivative. And they are all related to the Laplace transform of the function. And that's why this method is quite powerful, because giving an expression that has many derivatives of a function, we can basically transform that. Of course, we're using other properties that we already discussed in the last lecture, which is that when you have an addition of functions, the Laplace transform is the addition of the Laplace transforms. So transforming an addition is like adding the individual Laplace transform. So now we want to give some examples. So we're going to do a few examples for you, considering the properties of the Laplace transform. So let's first starting considering a differential equation that represents some physical phenomena. I could clearly say what is this physical phenomenon, but we're going to just restrict ourselves to the function, to the differential equation. So imagine that I have the second derivative of a function plus omega squared times the function equal to an independent function. And of course, I'm giving the two initial conditions, the value of the function at the beginning and its derivative at the beginning. In fact, this is always necessary when you're solving differential equation. The initial conditions is very important, because you're going nowhere if you don't have the initial conditions, right? You can have an idea about the solution, but only the initial conditions will really give you the solution for the problem you are considering. Very well. We're gonna now take the Laplace transformation of the whole equation. And we're gonna name it y, capital Y, the Laplace transform of this small y function. So since we learned that the Laplace transform of addition of two functions is the addition of the individual Laplace transform of each function, first we needed to take the Laplace transform of the second derivative of the function. But we learned before, as I told you, that the Laplace transform of the second derivative of a function is s squared times the Laplace transform of the function minus s times the value of the initial condition of the function minus the initial value of the first derivative. So if we use that, then this Laplace transform of y double prime, which is the second derivative of y, is s squared times y, capital Y, that now is the Laplace transform of y, small y, minus s times the initial condition minus the initial condition of the first derivative. Those are given values. Those are the initial conditions. Plus omega squared times the Laplace transform of the function itself. And this is equal to the Laplace transform of this function, which is not, you see, this function is important, but is a well-known function. The question mark here is y. We are trying to determine the y function, the small y function. And capital Y, S, is the Fourier transform. And the is Laplace transform. And the Laplace transform of this R function here, R of t, is what we're going to call capital R of S. Right. So we have this. This now is a very powerful algebraic. There is no more derivative in the thing. This is an algebraic equation, right, involving this part, where this is a well-known stuff. It's a function of S. And this is the Laplace transform. But you know, it appears here and here, so I can solve this algebraic equation for capital Y. If I do that, of course, I'm going to take S squared plus omega squared in one side times capital Y, and this is equal to S of Y of 0 and Y prime, small y 0 and small y prime 0, right, plus R of S. So, isolating, solving this equation for capital Y of S, we have this. This is the solution for Y of S, which is the solution for, is the Laplace transform of the solution of the original equation, which is the small y of t. Then we identify this. Now we just needed to apply the inverse Laplace transform, or just, you know, identify here what is what. If the small y of 0 and the small y prime of 0 are two values. I put k1 and k2 as value, numerical values here, right? So if we do that, we easily identify what is the solution, right? The Laplace transform of the solution, and by doing the inverse, right, we say that small y of t is the inverse Laplace transform. Maybe yellow is no good here, so let's use a more sharp color. So the inverse of Laplace transform of capital Y of S that we just got from the algebraic equation is the solution of your equation. Normally, by looking at this expression, you are able, by comparison with a table of Laplace transform, like this, you see, like this, you can identify. So if I look here, I'm going to have here S divided by S squared plus omega squared. So you see that probably is a cosine here. Because if you look, see, this is the, I'm going to do now the inverse. But I already identified that S divided by S squared plus omega squared is the well-known Laplace transform of cosine. So this is a cosine. And then there is a constant divided by the same. That's a sine. Right? And then there is a function divided by this, and this will be the product of the original function with something. So, normally by looking to the expression of the Laplace transform of the solution, we can almost guess what is the solution, right? Okay, so then now we are in a very good shape, because by using all those equations we can solve the problem, right? By using all the information of those Laplace transformation, we can get the solution. So this is an example. Let's get into a more numerical example. So let's write any equation that we want, right? So here I choose one that I like. So let's take this equation. This is the differential equation that now we want to focus on. It's a second order homogeneous ordinary differential equation, and it is giving to us the initial condition. So here they told us that whatever is the solution in the 0 is the value is 0, and at The first derivative in 0 is 2. And now we have to apply the Laplace transformation of this equation, right? And that must be equal to 0. And we know that the Laplace transformation of the second derivative is s squared times the Laplace transform of the function minus here, that will be s times the value of the function at 0, that's 0, so I did not put. And then minus the value of the first derivative. And the first derivative is 2, so minus 2. And the Laplace transform of 9 times y is 9 times the Laplace transform of the function y. And this must be equal to 0. So I got here in one step, simple step, I got my algebraic equation, which solution provides, of course, the Laplace transform of the solution I'm looking for. So isolating y, then I have y of x, capital Y of x, which is the Laplace transform of small y, times s squared plus 9 is equal to 2. I just put the 2 on the other side. Therefore, divided by s squared plus 9, I got what is the Laplace transform of the function. What function? The function that I'm looking for. The function that is solution of the original equation. So now, what I need to do is just doing the inverse Laplace transform. But normally it's easier to look. Of course, this has to do a constant divided by s squared plus something that easily identify as a cubic, as a square of something. If you apply, if you use the Laplace method a few times, you get so used to that you can more or less identify very easy what is the function. So let's look into this function. Here it is. That's the Laplace transform of the function I'm looking for, right? And if I look to my table, well, there are here, this function here looks like closer to the one I want, because the Laplace transform of the sine function of omega t is omega divided by s squared plus omega squared, right? So only looking to this table, I already identified that this probably has to do with a sine function. But to be more clear, I'm gonna just do the following. I'm gonna put 2 divided by 3 and write this as 2 divided by 3 times 3 divided by s squared plus 9. And we all know that 9 is equal to 3 squared, right? We all know that. So actually this solution is equal, oh, I wrote in the place that I shouldn't, but now I have to fix it. This is equal to, if I want to re-express this, right, I'm gonna write here so we can see clear. So this is equal to 2/3 times 3 divided by s squared, which is the reciprocal variable, so nothing I can do about it, and 3 squared. In the place of 9, the way I wrote, here I have the square of here. And why I did that? Because immediately I identified that if I have a Laplace transform of a function that is omega divided by s squared plus omega squared, this must be a sine function. And who is omega here? Omega is equal to 3. Of course, it has units and everything, but we're not worrying about this at the moment. Therefore, immediately, I write that the solution of this equation with those initial conditions is this one. It's 2/3, which is the amplitude. Whatever I'm analyzing, of course, I'm analyzing here. We all identify that this is a oscillation type of equation, right? It's oscillatory motion of something not driven by any force. So this is the amplitude, and this is omega. You know, the initial conditions is very important in the Laplace solution, because without that, my Laplace transform of the equation will depend on values that I do not have. I have to rely on initial conditions to be able to do that. And this is the solution of the problem. So now I have the solution, you see, in 2 steps. Normally, if I try to guess that the solution of this is, you know, I know that you know well the solution of this simple equation, but I'm just showing to you how is the methodology, how we use the Laplace transform to solve such equations, right? And of course, this is even more important when we are dealing with a more complex, more sophisticated type of equation. So let's imagine I have an equation like this. That's a little more complicated equation, right? Here it is. I have an equation that is a second order differential equation, ordinary and homogeneous, because that is 0. And I have 2 initial conditions as necessary for a second order differential equation to be solved. And this is the equation. That's the equation. What I'm going to do with this equation? Well, you know already that I'm going to take the Laplace transform of the equation itself. That's the way, that's the method. Take the Laplace equation of the function. And then the Laplace transform of y double prime is s squared times the Laplace transform of x minus the value of the function in 0 times s, so it's minus 2s, and then, here there is a minus, okay? So just so not to be confused. Minus, right? Here will be the value of the function, the first derivative of the function, which is minus 4, minus 4 is 4. So this here is basically the Laplace transform of this term. Now 2 times the Laplace transform of the first derivative, which is s times the Laplace transform of this function minus the value of the function in the point 0, which is 2 minus 2. And plus 5, the Laplace transform of the function itself. And this has to be 0, because the Laplace transform of 0 is 0. So this here is the Laplace transform of this, and the last term is the Laplace transform of that. So then I have my algebraic equation, which is composed of a new function, y, capital Y, that we know is by definition the Laplace transform of the function y. We solving this equation, you know, we're going to have s squared plus 2s plus 5 multiplying by capital Y. And then this whole thing will be equal to 2s minus 4 on the other side. So I have a s squared plus 2s plus 5 times capital Y, which is This is everything multiplying y. And then this is equal to, I have minus 4 from this part. You agree? I have, here I have minus 5. Here I have 4 times 4. And then here I have minus 4, so that cancel. That disappear. And then I have this is equal to the independent term, which is 2s. Only this 2s goes to the other side, 2s. So this is what I have. Right? And I can write this. You see? I have to rewrite this. And I'm going to do that. You see? So you understand what I wrote here. This term here is equal to s plus 1 squared plus 4. Because if I put s squared plus 2s plus 1, this is s plus 1 squared. And then plus 4 to give the 5. So I just rewrote this that way. Therefore, y of x is equal to 2s, which is in this side, divided by all this, by s plus 1 squared plus 2 squared, which is 4. And if I look around, if I look to my table now, wow, do I have a s divided by s divided by s plus 1 squared plus something squared. Well, this is almost this, but not quite. Here, 2, but then I have a s displaced s in this case for the cosine. But what I can do is manipulating a little bit this by adding and subtracting, making things to look perfect. So I want to transform this s in s plus 1 because then this is solved using the properties. So this expression can be rewritten as this one. You can verify easily because if this one is 2s plus 2 minus 2 with 2s divided by this term. Now I identify here a s plus 1 divided by s plus 1 squared plus 2 squared. And that sounds like cosine. But cosine displaced by 1. You agree? And we learned before that a function that is displaced by 1 is like having a multiplication by another function. Remember, I showed to you on our properties in the last lecture, I show you that this property, when we multiply by something, is displacing the s in the function. We know part of the things here. I just copying from my table that the Laplace transform of cosines of 2t is equal to s divided by s squared plus 2 squared. And I know that, so the inverse Laplace of this is the cosines, okay? And I know also that when I don't have the s, I have only 2 divided by s squared plus 2 squared. The Laplace transform of sine of 2t is this. Therefore, the inverse Laplace transform of this quantity here, 2 divided by s squared plus 2 squared, is sine of 2t. I know that. Because now I look to this and say, well, this is a displaced cosine. And is displaced using the property that when we multiply by exponential cosine, we get s displaced. Here we have to identify, right? Because here will be plus 1. So a here is minus 1. That's all. Right? A is minus 1. And then I already identified that this is an exponential of minus t times the cosines of 2t. And this one is just the sine of 2t. So I already, more or less, identify who is the inverse Laplace transform of this. Because now I know this capital Y, and I'm going to identify the inverse Laplace transform. And this part here, I already identify as being the exponential times cosines, and this is the sine. Right? I also displace it by 1. Because you see, when I displace by 1, it's like if I put minus 1 here, minus 1 here, minus 1 here in the S, is like multiplying this by my exponential of minus t. I showed to you, right? So the inverse Laplace transform of this is 2 times exponential of minus t cosines of 2t. So this is the exponential minus t, because the exponential causes the displacement of S by 1 unit. As we verify in the last lecture. We did not deduce all these because these are in books and everything, you know. You can use it with big security. We are not telling you a lie, so it's fine. You can use it. And this is, so you identify that this is the cosine times the exponential minus t. And this is the sine times the exponential minus t, because the S is also displaced by 1. So this is then showing immediately to us in an easy way that the solution, you know, when I take the Laplace transform, now I'm going to take the inverse Laplace transform of that expression, I get the solution. And the solution is 2 times the cosine minus sine. Incredible, because I identify these solutions here. Identify the functions which will provide to us that kind of expression for the Laplace transform. Right? Easy. Then I can easily write the solution for you. And the solution of the problem is this. Exponential time 2 times the cosine of 2t minus sine of 2t. Or, if you want to express this in a more elaborated way, you say that this is 2 times the exponential to the minus t cosines of 2t minus the exponential of minus t times sine. So this is a combination of oscillations with different amplitude, but with the same decay with respect to the variable t. So you see, is once you get the mechanism of applying the Laplace transform to solve your equations, it's easy. But you have to keep with you a table like this. That's important to know how to solve equations by Laplace. You must have this chart with you, because many of the functions that will come in equations are either power or cosines or product of them, and it's exponential and so on. So it's nice to have this chart with you, right? So you must have this function, Laplace transform, function, Laplace transform, all here. And with that, with this simple table, we solve almost many of the differential equations we have. Of course, I'm not telling you, you know, because after all, by experience, when you have an equation like this, you more or less identify what has to appear. When you have second derivative, and the function, that indicates that you're going to have oscillation. And when you have the first derivative presence, that mostly like to indicate exponential decay. And here it is, the solution. So you see, we transformed the equation, we took the Laplace transform, we solved the algebraic equation, we identified the Laplace transform of the solution, and then we did the inverse Laplace transform. And normally it's good to have the table, because in practice, you don't want to do by step. You look and you say, oh, I identify this, and knowing the main properties of the Laplace transform, you immediately write the solution. So you see, that equation, y double prime plus 2y prime plus 5y equal to 0, with the initial conditions of y of 0 equals to 2 and y prime of 0 equals to 4, has the solution. All the ingredients, all the initial conditions are here. When you're doing the Laplace transform, all the initial conditions are taken into account together when you're writing the solution. That's fantastic, isn't it? That's very good. And you can do then other examples. I was just putting here, this is a case of a mass connected to a spring with initial conditions. You take, that's easy, you take the Fourier transform, the Laplace transform, you get the equation, you just solve this by the Laplace, immediately you identify the solution. So this is like transforming, solving differential equation in very simple algebraic equation, and we can write so this differential equation. So this is an example of the last equation I solved. This is a driven harmonic oscillator, and with these initial conditions, and then I do easily. This is the equation. I call k. I divide everything by m, and I call omega 0 square is equal to k over m. And then the equation is rewritten that way. And then when you take the Laplace, now you need to take the Laplace of the whole equation. You take the Laplace of the whole equation. That you end with the Laplace of the second derivative plus omega square, the Laplace transform of the function, and this is equal to the f0 over m times the Laplace transform of sine of pt. P, I put p here because not to confuse with omega and everything. And by doing this, which is trivial, this is trivial to do, this will give you the Laplace 2 times, right? The Laplace transform of y, and then will appear the initial conditions, plus this, equal to that. You know what is the Laplace transform of sine, and then you put in here, you get the solution immediately. And the solution for this problem is this, right? You have a system that oscillates with the natural frequency and with the frequency of the pump. This is the pumping element for your driven harmonic oscillator or mass hanged by a spring. So you see, there are many methods of solving differential equation, but Laplace is the champion. If you get used to it, you solve easily equation. And normally most of the equation we're gonna deal in courses or even in problems, they are related to oscillations, they are related to damping, and therefore by knowing the functions that I present to you and the Laplace transform of those functions, you more or less are in good shape to solve most of the differential equation you're going to find in problems related to biomedical engineering in general. Of course, there are more complicated equations, but then once you know the mechanism, you know to solve, it's easy to apply and to make sure you get the solution. Well, I hope you like this short tutorial. Tell your friends. We're going to put it in the YouTube, of course, but is a tutorial in 8 lectures, short lectures, that put you somehow update with the most important. There are more related to differential equation that we did not cover in this short tutorial, like the solution of system of differential equations, which we apply Laplace, is easy to solve. Easy. It's like to solve the system of equation with 2 independent variables. Easy. And we have other methods to solve differential equations that are important. If we have a non-ordinary differential equation, have partial differential equations, we also have a collection of methods to solve them. But that comes in another tutorial that you'll be able to find soon. Thank you very much. See you next time. Bye-bye.